In this talk, I'd like to present our work on multi-core parallel clustering. Specifically, I'd like to show our clustering algorithms that can process billion-edge graphs in just a few minutes using a single machine equipped with multiple CPUs. Scaling up graph algorithms running on a single machine using parallel algorithms has recently been an active area of research. This is a plot from a SPA paper from 2 years ago, which shows that basic graph algorithms on a graph of over 200 billion edges can be solved in under 3 minutes using commodity hardware. Single machine parallel algorithms can be not only fast, but also very cost-effective. This plot compares different implementations of connected components. The y-axis shows the running time, and the x-axis shows the number of threads used by each implementation. And we can see that the single machine implementations, marked in green, are both faster and use orders of magnitude fewer threads than the best and the state-of-the-art distributed implementations, marked in orange. Our goal is to develop similar algorithms for clustering. Now, clustering is a complex problem. The running time of the clustering algorithms is typically higher than, for example, the running time of connected components implementation, and the input is a weighted graph, which implies that the input size is noticeably larger. Now, this is a big challenge because fitting the input in the local memory of the machine that we're using is actually one of the big difficulties in scaling up single machine parallel algorithms. Still, we're able to develop parallel clustering algorithms that can handle graphs of billions of edges on a single machine, and in this talk, I'd like to present two of them, affinity clustering and correlation clustering. Our implementations, as well as the research results that I showed in the introductory slides, are based on the GBBS framework. This is a C++ library that provides an efficient graph representation, low-level parallel graph primitives. For example, apply this function to all edges of the graph in parallel. GBBS also provides a parallel scheduler using work stealing, and this means that executing parallel nested loops is very efficient, and we can get the most of the available CPUs. And finally, the primitives in the GBBS framework have good theoretical properties. They are work efficient and typically have polylog depth. The first parallel clustering algorithm that I'd like to show is affinity clustering. This is a clustering algorithm of weighted graphs that we actually mentioned in the first section of this workshop. But let me quickly repeat how it works. The basic principle is that each node should be in the same cluster as its most similar neighbor. And specifically, the algorithm repeats the following steps, shown in the picture below. First, we mark highest weight incident edge of every node. It's marked in orange in the picture. Then we find connected components of the marked edges. These components define the clusters. And then we contract each cluster to a single node and repeat the algorithm. Now, when we contract each cluster to a node, if we had multiple edges between two clusters, these edges are merged into one, and the weights of these edges are merged into the weight of the final edge by using a configurable linkage function, for example, maximum or average. So the parallel implementation works as follows. The first step is very parallel by its very nature, so that's pretty easy to parallelize. For the second step, we use an implementation of connected components from the GBBS library, and the third step is actually not too difficult once we have an efficient sorting primitive, which is also available in the GBBS framework. So what is interesting or important is that the parallel implementation computes the very same results as a sequential one. Why do we want to have an efficient implementation of affinity clustering? One reason is that affinity clustering delivers very good clustering quality. So this table compares clustering results from affinity clustering to 3 other popular algorithms, and we can see that on this collection of data sets, affinity clustering typically delivers the best results. Here the numbers indicate clustering quality, and higher means better. So thanks to our parallel implementation, not only we can compute high quality results, we can also compute them fast. In particular, for a graph of almost 2 billion edges, we can find a clustering in a bit over 10 minutes, which is almost a 9x speed up over the serial baseline. For 2 billion edges, the implementation uses around 200 gigabytes of RAM, which means that on a machine with 1 terabyte of RAM, we can hope to cluster a graph of up to 10 billion edges. The second algorithm I'd like to talk about is correlation clustering. Here, the input is a graph with positive and negative edge weights. A positive edge means that the endpoints should be in the same cluster, and the negative edge means that endpoints should be in different clusters. So the specific objective that the algorithm attempts to optimize is to maximize the sum of edge weights within clusters. These are the edges marked in orange in the picture. So in this example, the objective of this particular solution is 9 because we add up the weights of the orange edges. So 4 plus 2 plus 3 gives 9. And we can also see that obtaining a perfect solution, one in which each positive edge is within a cluster and each negative edge goes across clusters, is not always possible, which makes this problem challenging. And actually, in theory, it is known that finding an optimal solution is hard. Still, there are some algorithms that work well in practice. So let me show you one algorithm that we will then parallelize. So in this algorithm, we start with each node in its own cluster, and then the algorithm alternates between two phases. In the first phase, each node finds its best move, which means it moves to a cluster chosen such that the increase in the objective is maximized. And then the node moves to this chosen cluster. Then the second phase works similarly, but in that phase, the clusters find their best moves, and that means that for each cluster, we'd like to merge it with another cluster, again chosen such that the increase in the objective is maximized. Now, if for a given node or cluster, no move increases the objective, then the respective node or cluster does not move, and if no node or cluster wants to move, the algorithm terminates. The parallel implementation performs these steps in parallel within each phase. So first, within the first phase, each node finds its best move in parallel, and then all these moves are applied again in parallel. Now, there is a small difference between this implementation and the serial one. In the serial one, each node worked or decided on its best move depending on the best move made by the nodes that moved before. Here, all nodes choose their best moves independently, and they're unaware of how other nodes are going to move. And then all those chosen moves are applied at the same time. So the results of this algorithm can be slightly different from what a sequential implementation gives. And in particular, some of the moves may decrease the objective because a node moving to a cluster is not aware of other nodes that may be joining that cluster. So when we implemented this algorithm and evaluated it, in addition to the running time, we also studied the objective value. And we can see that the parallel implementation returns a clustering whose objective is typically few percent of what the serial implementation gives. And compared to the serial implementation, we get a speed up of roughly 4 to 5x. And in particular, we can cluster a graph of around 1 billion edges in around 5 minutes. So let me quickly summarize. We've seen how implementing scalable parallel single machine algorithms is an active area of research, and this is because single machine implementations can be both faster and cheaper than distributed ones. I've shown you a couple of clustering algorithms that scale to graphs of billions of edges, and then we obtained from 3 to 9x speedups compared to the serial baselines. And if you'd like to try out our clustering implementations, here is a link to our GitHub repository. Thank you.